Alright, today we're going to multiply polynomials. Really, we're going to use binomial expansion to expand binomial expressions that are raised to positive integer powers. That means we're going to have a binomial, which is two terms, raised to a number. So first of all, to multiply a polynomial, use the distributive property and the property of exponents. We're going to do some really simple ones first, which will be a monomial times a binomial, monomial, one term, binomial, two terms. And we're just using the distributive property. So you multiply the coefficients, 4 times 1 is 4, and your variables, you add the exponents. You have to remember all those properties that we reviewed earlier this year and that you learned in Algebra 1. So 2 plus 2 is 4. 4 times 3 is 12, 2 plus, there's no y term here, so we just get the y squared term. Next one, we distribute all the way through the parentheses. Fg times f, the f's, you add the exponents together, you get a 5. There's no g term, so it's g to the first power. No coefficient, so the 2, 1 plus 3 is 4, g plus g, so 1 plus 1 is 2. Negative 3, f, both 1's, add them together to get 2. G to the first power, g to the third power, add together to get 4. So when you have a monomial times a binomial, or a monomial times a polynomial, binomial, polynomial, you just distribute that monomial through, and you have to remember your properties of exponents. So multiplying two polynomials. So here we have a binomial and a polynomial, binomial and a polynomial. Use the distributive property and multiply each term in the second polynomial by each term in the first. So if you see the x, I distribute through the polynomial, and then the 2 I distribute through the polynomial. And you'll see red, so x, 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 and then 2, 2, 2. You might have to pause here and look at the math and make sure you understand where all the numbers come from, and that's fine. So I distribute the x through the polynomial, and I get x times x squared, x times 4x, x times negative 3. Then I distribute the 2. 2 times x squared, 2 times 4x, 2 times negative 3. I actually wrote everything out. X cubed, 4x squared, negative 3x, 2x squared, 8x, negative 6. And then I collect like terms. You may want to, as you're collecting like terms, cross them off. We always write them biggest exponent to smallest. Cross it off when you write it down. When you add those together, cross them off. Add these together, cross them off. And then you're left with that. Once everything's crossed off, you know you're done. You know you've collected all the like terms, and you're done multiplying your polynomials. Let's try another one. I distribute the a times 2, a times negative 5, a times a squared, negative 3 times 2, negative 3 times negative 5a, negative 3 times a squared. Do all your multiplication. 2a, negative 5a squared, a to the third, negative 6, positive 15a, negative 3a squared. Collect your like terms and you have your answer. Again, as you're adding them together, it might make better sense to cross them off as you go. When they're all crossed off, you know you have the answer. Okay, harder. I'm going to let you guys look through that. My distributing arrows are sort of crazy, which is what the yikes stands for. I distribute all the way through. It's all color coordinated, but to step through it, you get a really long answer. I mean, it condenses down to a short one. Notice I have the highest exponent down to the lowest. But here I want to show you that we can use a different method for multiplying those big polynomials. We're going to set up a table. If you like to work the math this way, that's fine. And there's absolutely nothing wrong with it. As usual in math, there's more than one way to do a problem, which is good and bad. same problem method 2. I've got the exact same problem, red and green. We're going to use a table to organize. I think the table is really great. If you see, I wrote the red one, y squared negative 7y and 5. The green one, y squared negative y negative 3. I just use that table and do the multiplication. Y squared and y squared is y to the 4th. Negative 7y and y squared is negative 7y cubed. I have y to the 1st power y squared. 5 and y squared is 5y squared. Same thing. Okay? Negative 7y and y. Negative 5, sorry, positive 5 and negative y. Same thing. Okay, fill in the table. The top left corner of the table is the first term in the product. Combine other terms along the diagonals. When you have all of the variables, y to the 2nd, y to the 1st, y to the 0, y to the 2nd, y to the 1st, y to the 0, your diagonals will always work out to you be able to combine them. If you're missing some, you may not be able to use the table, and we'll get into some examples like that in person. But I can combine all my diagonals. Y to the 4th, negative 7, negative 1, 5, 7 is 12, negative 3, negative 5, positive 21, and negative 15. So it's a much more condensed problem, and I think much more easier to handle. There aren't, a huge long line of constants, variables, coefficients, etc. So you can choose which way you'd like to do the work. Let's try an application problem. A standard box is p feet by 3p feet by 4p feet. A large box has 1.5 feet added to each dimension. Write a polynomial in standard form that can be used to find the volume of the large box. Volume is length times width times height. Okay, the length, p plus 1.5. The width, 3p plus 1.5. And the height, 4p plus 1.5. Okay, so we're going to multiply the length, the width, and the height. So this is the first time we've seen a problem like this. I'm multiplying 3 binomials together. The best way to do that is to do FOIL 2 at a time. I took these last two, I FOILed them. First, outer, inner, last, and that's what I got in purple. Then I took that polynomial and multiplied it by a binomial, which you'll see is a big long answer, but condenses down to this. You can absolutely set up a table to work this bottom problem, or you can write it horizontally, whatever you'd like. Another application. Mr. Silva manages a manufacturing plant. From 1990 to 2005, the number of units produced in thousands can be modeled by this polynomial, this function, The average cost per unit in dollars can be modeled by this function. Write a polynomial in tx that can be used to model total cost. That says total costs. So we have the total cost equals the number of units multiplied by the cost per unit. Okay, this I'm giving to you. Total cost equals number of units times cost per unit. I set up a table for this one because the numbers are a little messy and very small with a lot of decimal numbers in between decimals. So the top of the table is the number of units. 0.02x squared, 0.2x, and 3. And this line is the total cost, that function. Using your table, you're going to multiply where the row meets the column, and then collect all your like terms. 0.0008x to the 4th. Add these two together, I get 0.0028 negative. Add all of these together, I get 0.28x squared. Add these two together, 0.3x, and then 9 is your constant. So really, the application problems aren't difficult if you remember what we're doing. We're multiplying polynomials. And that's all we have for today.